Hello everyone, my name is Rohit,
My name is
My name
Chris.
my name is Zealand.
and today we will be introducing SIFT, which stands for Scale Invariant Feature Transform. So what is SIFT? Stands for Scale Invariant Feature Transform, and it is a computer vision algorithm used for feature detection and feature description across multiple images. The algorithm was first proposed in 2004 by David Lowe in his paper Distinctive Image Features from Scale Invariant Key Points. Before we talk more deeply about SIFT, I will give a brief overview about computer vision. So, computer vision is a field of study that involves training computers to interpret the content of images and videos. Common applications of computer vision include object recognition, image alignment, image retrieval, and stereo imaging. In general, accomplishing most of these tasks requires finding matching points across several images or viewpoints, and these points are known as features. A feature can be any part of a digital image which is needed for the completion of a certain task. So if we are doing image matching, for example, your features would be points that are visible in both images. Features can be image patches, corners, edges, or specific object points. And as is shown in figure 1, the white piece of paper is used as a figure. It is important that all features are uniquely identifiable because you do not want to falsely match features in different views. So for example, the feature shown in this image is uniquely identifiable because there's only one, one patch of white paper. However, if we were to use the brick background of the building as a feature, that would not be uniquely identifiable because there's like multiple patches of brick. And edges wouldn't work either because anywhere along the edge is anywhere along an edge is defined as an edge, but corners would work because there will only be one corner in one specific location. The feature matching process consists of three main steps: feature detection, in which all points of interest are first identified; feature description is when the region around the feature point is described in a way that can be understood by the computer, and it is then stored in a descriptor vector; and then feature matching, when feature descriptors across different views are compared to find similar features. Feature descriptors must provide some invariance to geometric, so translation, rotation, and scale, and photometric, brightness, exposure, differences between images. This will be shown using the importance of that will be shown using the Harris corner detector as an example. The Harris corner detector is a feature detector which is invariant to rotation but not scale. We have two objects shown in the figure at different scales. One object is smaller and one is larger. Each object has equal sized windows used to detect features from the object, so feature matching could be conducted. In the larger object, the feature matching windows can only see a line segment of the object, so it defines them. It defines the features as edges. While in the smaller scaled object, the feature matching window sees the entire object and labels it as a edge, as a corner. Sorry. So feature matching in this case could not successfully be accomplished. The shortcomings of the Harris corner detector and other feature detection algorithms prompted the development of SIFT. SIFT image features are invariant to image scaling and image rotation. They are also partially invariant to changes in illumination and viewpoint. And to implement SIFT, it consists of five main steps. The first of which is scale space extrema detection. The next is key point localization. Third is orientation assignment. The fourth is key point descriptors. And the fifth is key point matching. I will begin by talking about scale space extrema detection. So key points whose descriptors are invariant to image scaling must first be detected by identifying locations and scales which are identifiable from different views of the same object. To accomplish this, features which are stable across multiple scales must be found using a continuous function of scale. And it has been shown that this function of scale must be based on the Gaussian blur operator, which allows for images to be scaled without introducing any false details. So in this figure, we have an example of the scale space used to find those features. The scale space is generated by taking the original image and progressively blurring it. These blurring levels are known as the image scale. So in this example, we have 6 levels of blurring, and and then images of the same size but of different scale levels are called octaves. You can have any number of scales and octaves as you like. However, the original author of the SIFT paper recommends 4 octaves and 5 scale levels for optimal performance. For scale space extrema, more about scale space extrema detection. The scale space we just showed is defined as the convolution of the Gaussian blur operator and the image, as is shown in the equation, where L is the blurred image, I is the original image, X and Y are the location's coordinates, and sigma is the scale value, or the blurring value. And G is the Gaussian blur operator given by the equation at the bottom. And the difference of Gaussian's technique is then used to enhance features and find stable key points in the scale space we defined. And by enhance features, I mean make corners and edges more prominent. The difference of Gaussians is given as the difference of 2 blurred images, with one image having a scale k times the other. So as you can see in the equation below, one image is a function of sigma and one image is a function of k times sigma. Using the difference of Gaussians, extrema are detected by comparing each point with its 26 neighbors. So on the left side of this image, you can see the difference of Gaussians, how different scales are subtracted. And then on the right side of the image, you can see how extrema will be detected, where X is the pixel we are interested in, and the green circles are all its neighbors. The pixel we are interested in is compared to its 9 neighbors in the scale above, 9 neighbors in the scale below, and 8 neighbors on the same scale. If the pixel has the smallest or greatest value, it is labeled as an extrema. And now Chris will talk about key point localization.
So key point localization. After the scale space extrema detection, this will produce too many key point candidates. The next step is to perform a detailed fit to the nearby data for accurate location, scale, and the ratio of principal curvatures. So the image below shows the prior to the key point localization and just after the scale space extrema detection. So as you can see, we have a lot of points that needs to be eliminated. Next slide. The interpolation of nearby data for accurate position. This is the first step. So for each candidate key point, interpolation of nearby data is used to accurately determine its position, where the interpolation is done using the quadratic Taylor expansion of the difference of Gaussian scale space function, which can be shown in the equation below. Now, where d and its derivative are evaluated at the candidate key point, and x is the offset from this point. The location of the extremum is determined by taking the derivative with respect to x and setting it to 0. If the extremum is greater than 0.5 in any dimension, that means that the extremum lies closer to another key point. Then, if that's the case, the key point is changed and interpolation is performed again about the new key point. Otherwise, the offset is added to its candidate key point to get the interpolated estimate for the location of the extremum. Next slide. Next step is to discard low contrast key points. In order to discard low contrast key points, the value of the second order Taylor expansion is computed at the offset. If this value is less than 0.03, the value is discarded. Otherwise, it is kept with the final scale space location, which is the original location plus the offset. The image you see below is the the image that we started with, but after low contrast key points have been discarded. Next slide. Final step is eliminating edge responses. The difference of Gaussian function will have strong responses along the edges, even if the candidate key points is not robust to small amounts of noise. Hence, the key points that have poorly determined position and yet high edge responses must be eliminated. This is done by finding solving for the eigenvalues of the second order of the Hessian matrix, which is a matrix you see below. The eigenvalues of H are proportional to the principal curvatures of D. It turns out that the ratio of the two eigenvalues, let's say alpha as the larger and beta as the smaller one, as shown in the equation, the ratio, which is alpha over beta, is sufficient for SIFT's purposes. The trace of H will yield us the sum of the two eigenvalues, while its determinant yields the product. The ratio given by R can be shown to be equal to lowercase r plus 1 all squared over R, where this lowercase r is the ratio of alpha over beta as described before. This depends only on the ratio of the eigenvalues rather than their individual values. Capital R is minimum when the eigenvalues are equal to each other. Therefore, the higher the absolute difference between the two eigenvalues, which is equivalent to the higher absolute difference between the two principal curvatures of D, the higher value of R. This follows for some threshold eigenvalue ratio R, which is in popular usage it's 10. The R for the candidate key point is larger than R plus 1 all squared over R. That key point is then recognized as poorly localized and hence rejected. Next slide. Next step is orientation assignment. In this step, each key point is assigned one or more orientation based on local image gradient direction. This is an important step in achieving invariance to rotation, since key point descriptor can be represented relative to this orientation and thus achieve invariance to rotation. Next slide. Now, for each image sample at this scale, the gradient magnitude and orientation is pre-computed using the pixel differences as shown in the equation below. Next slide. Now, in order to do the actual orientation assignment, a neighborhood is taken around the key point location depending on the scale, and the gradient magnitude and direction, as described in the equation in the previous slide, is calculated in that region. An orientation histogram with 36 bins covering 360 degrees is created. So from 1 to 10 degrees, it's one bin, 10 to 20 degrees, it's another bin, 20 to 30 degrees is another bin, and etc. So for example, if the gradient direction at a certain point is 18 degrees, it will go in the 10 to the 20 degree bin. This amount is added to the bin is proportional to the magnitude of the gradient at that point. Once this is done for all the pixels around the key point, the histogram will have a peak at some point. So the histogram you see on the right shows you for a sample image what you would get. Now, at this stage, the highest peak in the histogram is taken, and any peak above 80% of it is also considered to calculate the orientation. Next slide. In the following slides, Zelin will talk about the key point descriptor.
The descriptor is the final stage of the scale invariance feature transform algorithm before the matching process. This step will create the invariance functionality to the image that its location, scale, and rotation will be invariant during the transformation process. From the previous steps, we could find out the location at particular scales of each feature points and assign orientation to them. The key point descriptor is going to create a set of orientation histograms on a 4x4 pixel neighborhoods. with 8 bins inside each pixel. These histograms are computed from magnitude and orientation values of samples in a 16 by 16 region around the key points, also known as gradient angle histograms. The dimension of neighborhoods is dependent on the feature point scale, and each of the spatial bin contains an angle histogram divided into 8. Thus, we have totally 128 elements in the entire vector. Since the 4x4 spatial grid is centered on the feature point and rotated to the orientation determined for the key point, the scale of the grid should be corresponding to the scale of the key point. Next slide. Sorry, can you go back to the next previous slide? From the left figure, we could assume the 16 by 16 region is centered by a key point feature, and we could break it down into 4 subregions of 4 by 4 pixel. The graph only shows 2 by 2 in this case, and normally it should be 4 by 4. And there are 8 arrows in each pixel. These represent the gradient angle, contains information of magnitudes and orientation values of samples. The right figure illustrates the histogram. 8 bins come from each pixel. Next slide. As shown in this slide, there are 16 orientations from the pixel of the cells, and they all ended up in 2 bins, which 11 in one bin and 5 in the other. So totally we have 16 orientations stored in the bin. Next slide. The weight of each pixel is provided by the magnitude of the gradient, as well as a Gaussian center on the feature point, where the delta value equals 1/2 the width of the descriptor window. As shown as a blue circle, can you go back to the previous slide? As shown as a blue circle. Next slide. The purpose of the Gaussian window is to avoid sudden changes in the descriptor with small changes in the position of the window, and to give less emphasis to the gradients that are not too far from the center of the descriptor, as these are most affected by misregistration errors. Next slide. Finally, the feature vector is modified to reduce the effects of illumination change. A threshold of 0.2 was chosen to apply, and again, the vector is normalized to unit length. The normalization process could cancel the multiplication of pixel value by a constant caused by the change in image contrast, which known as illumination effects. The threshold process is also referred to as clamping, and it can improve matching results even when nonlinear illumination effects are not present. Through different experiments, it is proved that the feature matching accuracy is above 50% for viewpoint changes of up to 50 degrees. Therefore, SIFT descriptors are invariant to minor affine changes as well. Next slide. Once we complete all the previous steps, here comes the feature matching process. The results will be produced directly in this stage, and here are the 3 algorithms that form up the matching process. Nearest neighbor matching of local image descriptor is the most basic form of feature matching process, which they use the computed image descriptor from 2 images and find the point in the other image domain that minimize the Euclidean distance between the descriptor represented as 128 dimensional vectors. To have the best matches, we need to filter the ambiguous matches. To do so, we are going to set up a threshold on the ratio between the distance to the nearest and the next nearest points. which it must be less than 0.8. People will probably ask, since the nearest neighbor matching needs to compare the descriptor from two images, what if there are too many descriptors and it is going to take a long time? And here is a solution to it. So from that method, we could perform the feature matching process. However, this method implies large number of comparisons to the image descriptor stored in the database. And normally the process is slow. Therefore, we use the best being first approximation for selecting point matches to speed up the resulting nearest neighbor matching. To increase the robustness of the image descriptors, a fine home transform-based evidence accumulation is used. This algorithm is used when we are applying the SIFT descriptor for object recognition. It used the triples of image matches to accumulate evidence for objects as represented by sets of interest points with associated image descriptor. Next slide. So these three images demonstrate the key point matching process as we described. In the third image, the black lines represent the matches of the interest points detected from the two images with the same thing. The blue and red arrows at the center of the circle illustrate the orientation estimates from the peaks in local orientation histogram near the interest points. And next, Rohit is going to introduce the key point object recognition and sum up the presentation.
So in SIFT, one of its main applications is object recognition. Object recognition is shown in the figures on your screen. Using model images for 3D objects, so the shoe, the telephone, and the bear, their outlines are extracted. Using the model outlines and image keys, object recognition is conducted, as is shown on the figure to the right. Another application of SIFT is image stitching. So we have two images here which are of the same location but taken at different viewpoints. Key points are first found, their descriptors are calculated, and then they're matched to create one final stretched image as is shown in this figure. In summary, SIFT is a computer vision algorithm used for feature detection across images. The SIFT algorithm is invariant of image scale, rotation, illumination, and viewpoint. And the SIFT algorithm consists of 5 main components. Scale space extremely detection, used to find scale invariant key points. Key point localization, used to get rid of unhelpful features. Orientation assignment, used to find rotation invariant key points. Key point descriptors, used to ensure invariance to image location, scale, and rotation. And finally, key point matching, which is used to match the features in each image. Here are references, and thank you for watching.